In this video, we're going to talk about two of the most popular safety analysis in safety critical industry, FMEA and FMEDA. There's always this question of uh, what is it that an FMEDA offers that an FMEA doesn't offer? So I'm going to try to explain the similarities and the differences and how we need both in a project. Both FMEA and FMEDA, they are safety analysis which are very popularly used in safety critical industry, be it aerospace, automotive, robotics. To start off, we can look at what the similarities between the two are. FMEA stands for failure mode effect analysis. FMEDA stands for failure mode effect and diagnostic analysis. They're both bottom-up analysis, also known as inductive analysis. Essentially, what this means is we start from the bottom given an architecture. So, in case of an FMEA, we're given an architecture, say a system architecture, a hardware architecture, a software architecture. We identify every component of this architecture, and for each of the components, we identify failure modes, what is the effect, and how do we mitigate the effects if it is considered undesirable. This is very similar to the FMEDA, wherein you have an effect, you have failure modes, you have components, you have failure modes, there is an effect, and then we try to come up with some mitigation mechanisms to ensure that the failure mode does not lead to the undesirable effect. The way this is done in FMEDA is a little different from FMEA. But the overall idea is that we want to improve the overall safety of the product and the overall diagnostic mechanisms that we have for failure modes. Now, how it gets different is in the way you can say the risk is calculated in FMEA versus FMEDA. Now, in an FMEA, the classical approach is we identify failure modes, and for each failure mode, we identify the risk in terms of severity, occurrence, and detectability. So a high severity, a high occurrence, and a high detectability will be a high risk, and that is denoted in the form of an action priority or a risk priority number. What this means is when we do the FMEA, we look at each failure mode. For each failure mode, we give a rating as to what the severity is. Safety critical, we say it's 10. If it's occurring very often, the probability of occurrence is very high, we get a 10. And then if there is no detection mechanism, then we probably say it's a 10. Now, based on the severity, occurrence, and detectability, we say, oh, the risk is very high. What can I do to lower the risk of this failure mode? Then we would decide there's nothing that can be done about the severity. Severity is severity. Somehow I have to lower the occurrence, which is I could use a trustworthy component to lower the occurrence, or I could do some testing during design to lower the occurrence. Then there's detectability. What can I do to lower the detectability? I can add some diagnostics to detect the failure and react to the failure. That way, I'm lowering the risk for an individual failure mode. So FMEA is focused on individual failure modes. FMEDA, on the other hand, is used to calculate risk in a different way, and it is used to calculate risk for the overall system. So we don't look at individual failure modes, even though we write down individual failure modes, but the goal is to find out risk at more of a entire component level. What that means is, at the end of the FMEDA, we try to identify these three parameters: PMHF, which is the probabilistic metric of hardware failure; SPFM, which is single point failure metric; and there is the LFM, which is the lagging failure metric. PMHF, what this tells us is what is the total probability of failure that will lead to a safety goal violation. In a system, you can have failures of 200 different components in 200 different ways. What is the probability that something can fail that can lead to a safety goal violation? So this is the overall probability of the entire system. We're not looking at individual failure mode, but all the failure modes that can lead to a safety goal violation. What is the probability? Then there is the SPFM. SPFM, or single point failure metric, it is a metric that tells us if there is a failure, what is the percentage of probability that this failure will fail safely or as a multiple point fault. What this means is if I have uh, if I have 100 failures in a system and 99% of the failures either fail safe or as a multiple point fault, then I have an SPFM of 99%. What this means is 99 of the times I don't have to worry. It's just that one time that may cause a problem. So that is the idea behind SPFM. So it tells you if there is a failure, what is the percentage that fails safely or as a multiple point fault. And a high value of SPFM is good. Then there is LFM, which is also called as a latent point failure. And a latent point failure essentially tells us if there is a latent point fault, how good is the system to detect it, or is it safe by design? So if you have 100 multiple point and latent faults, how many of those are detectable and safe? A high percentage of detectable multiple point and safe faults would mean if something goes wrong, it can be detected. So that is the idea behind the SPF and LFM. And notice that in both these cases, or even in the case of PMH, we are not talking about individual failure modes. We're talking about the overall system. This is an overall system metric. We're not talking about individual failure modes like the FMEA talks about, but we're talking about the ability of the overall system and all the failure modes of the system. That is the fundamental difference between the FMEA and FMEDA. FMEA focuses on individual failure modes. FMEDA focuses on the overall system. FMEA finds out ways to lower the risk of each failure mode, and FMEDA focuses on improving the overall metrics for the entire system. So to conclude, both FMEA and FMEDA are powerful techniques that can be used to identify failures and mitigation mechanisms. They both provide different types of information. One provides information at a failure mode level, and the other provides more information at the overall system. And both of them are necessary to ensure that we have a safe and a robust system.